Let's proceed with the next presentation, which is Andrew Kuess from ArcologyX talking about the Allmatter machine. And I think that's a good continuation of nuclear because he is splitting everything into atoms, right? Andrew, floor is yours.
Okay, just give me 1 second, just pulling up the presentation material here. How's everyone doing today?
Good, thank you.
Good, man.
Yeah, you're coming on.
All right. Hello, everyone. My name is Andrew Kuess. I've been working with Arcology Solutions now for over a year. I'm an independent researcher and long-term entertainer known as Star Captain Dread. I've created some books, I've created board games, I've created some music, and lately I've been doing a lot of science-related work to advance arcology research. In 2015, I actually campaigned to run for political office in Canada on a space-oriented platform. And over the last 5 years, long story short, I now live in America with my wife, and I'm working towards developing a infrastructure system that will help with lunar development, which I call the Allmatter machine. Presentation will basically cover the components of the Allmatter machine. This basically is a system that is a support system for arcologies. Arcologies are a system of design which integrate architecture and ecology to infuse as self-sustainable habitats that we could create on Earth or potentially in other remote locations, such as on the water, in the air, or on other planets. Other planets, when we go to try to colonize them, may be like Earth, they may not be like Earth. So having digital twins on Earth or physical twins that we could have as sister cities that could be across the ocean or on land in craters could allow us to replicate the environments that we would have on other worlds on Earth, enabling us to study how we would live in remote environments, such as on another planet that had an ocean body. How would we live on the ocean? And arcology at sea could help us to understand that process. So in order to build arcologies, no matter where they are, whether they are a space arc or they're built on land, it's going to take a lot of logistics and a system of logistics that we haven't developed yet to develop megastructures. So the Allmatter machine represents a framework that we could use to develop megastructures on Earth and also in other places. Essentially, it's broken down into two major components. There's mining nodes that feed into the main industrial complex. So the industrial yard would be broken down into different components that would essentially allow for in situ resource management for different materials. And as you scale in development, you gradually scale in your capacity to develop new products. At first, you would have things like structural materials, industrial basics, such as aluminum, aluminum oxide, copper, steel. You want to have the capacity to refine these materials in situ, even if you can't mine them, so that ultimately you don't need to ship your spoons to the moon. You can ship ingots of steel. And on the moon, they could then use that steel for whatever purpose that they need it for locally. They would also have the capacity to recycle that material. They would have the capacity to store that material. So we create a closed loop industrial system and we build it in a gradual manner, which I call these 5 phases that's kind of broken down in this process here, that goes from industrial basics to thermal and electric materials, fuel and propulsion, then high risk management materials such as nuclear, and then specialized manufacturing materials. Each one of these processes requires machinery, technology in order to operate and go through this process. So part of my mapping out this technology tree of the Allmatter is determining the process for each material going through its phase of management. So, for example, for crude wax, you can source wax from different plants. You can source wax from petroleum. In space, you're not going to find petroleum, but we could create an agricultural chemical complex that could grow the materials. We could have a refining system that processes those materials, and that would allow us to then use industrial waxes for many different purposes in space, and we could actually generate that. So we don't have to ship wax to the moon if we build this system and we generate these plants. This allows for in situ resource management of that material. And as we scale the development of this system, starting with low-cost materials to create epoxies, polymers, concrete, wax, then we move into metal refinement. We can start creating tools. You can use things like aluminum and steel together to create tools that are necessary on site, so that I'm not calling Earth and saying, hey, we need more hammers. We need, 100,000 tons of steel, and we can print all the tools that we need for our toolbox, and we can recycle it. So if we enable colonies to have a framework for in situ resource management on an industrial scale, then we're going to enable the actual capacity for them to operate on their own long term. So my research has kind of delved into how do we scale up this tree and how do we make this possible? Through the outlining of the system, essentially it's broken down, like I said, into mining sites that can be different locations on Earth. They could be in space. They could be craters on the moon that all feed into the central complex. The central complex could be built underneath any arcology to support its development, essentially as its logistics management system, so that any arcology anywhere would want to have this industrial base so that it can essentially rebuild itself and build new arcologies. It's not just a sustainable model, it's a sustainable, expansive model of civilization that we can use on Earth and also carry with us into space. So the industrial complex itself, which I call an industrial yard, is broken down into these different segments: the sorting and storage complex, metal refinery complex, the agrochemical complex, chemical factory, atmospheric separator, manufacturing complex, electroalloying lab, and then there's also novel material labs that will be built onto it later in later phases that could study things like lanthanides and actinides, which are rare earth metals and nuclear materials. So this kind of covers the mining operations that could feed into the Allmatter machine, depending on where the arcology is built and depending on what phase of development. It may have access to only planetary resources, but when you get to about the third or fourth phase of the Allmatter machine, it could feed into an orbital development system, like an orbital shipyard, that could enable the construction of megastructures in space. And that is ultimately the goal of this technology, is to enable a logistics system that would actually support an arc in space, which coincides with my research at the Lifeboat Foundation, which has a ARC-1 project that my arcology research kind of contributes towards. So my long-term research kind of is from land to sea to air and eventually space arcology research, and the logistics surrounding how we would actually from a material science basis make that happen. So this kind of touches on the mining operations. The next few images are just kind of a demonstration of where some of these mining operations might take place on Earth, on the moon, on Mars, as examples, and on asteroids. After that, we get into the sorting and storage complex. So first, anything that comes into the facility, whether it be by truck, whether it be by rail, whether it be by boat, would be coming into the central storage and sorting complex. And that's going to basically route your materials to different parts of the facility based on what it is. It may go to a storage complex that basically is a modular, expandable storage rack that can store elements or ores or compounds, essentially in a scalable manner that allows the colony to store all the materials that it would essentially need to feed into the Allmatter complex. You'd also have an ingot vault that would store metals of different types You could have a cryogenic storage vault that would basically store your atmospheric chemicals, and a recycling bay that allows you to process all of the materials that are being recycled to send them to the refinery complexes or to machines that are necessary to break them down. This is kind of a further outline of the complex's needs, some of the machinery that would actually be involved in this. I've broken down in some of the facilities how many workers would be necessary to operate the machine, so I kind of have an idea of how many jobs we could create with an arcology like this on Earth or on the moon. My current estimate is about somewhere between 250 to 300 people could be employed, or robotics could be used to operate these machines. Beyond the sorting and storage complex, you have a metal refinery complex, which has a receiving bay, smelting and separators, alloy formation zone, form conversion units, alloy ingot library, so that if you're creating new alloys, you have a library that basically can access, look about the information and what applications it may have. And there would also be a novel materials and experimental fabrication bay as part of the metal refinery, that as we get into more novel material development, this would be the place to manufacture those things. These are kind of slides that look at the process of how to refine the different source ores into the finalized product. This is it for aluminum and aluminum oxide, copper, magnesium. So I've kind of broken down these processes so that I could further understand what machinery is necessary for the calcination of diatomaceous earth and purification of it and then smelting, so that I can create an inventory list of the machines that we would need to basically pack into the Starship along with the resources and send it there. And then we can produce stuff on site. We don't need to send boxes full of spoons, as an example. Sodium, this is the resource flow for that. I basically broken this down for all of the first 10 materials in that phase list, and I'm continuing to expand upon them as my research expands. This kind of breaks down the agrochemical complex. So there's different types of chemicals that we could use to create plastics and polymers, because we can't get oil on other planets. We may need to have a substitute. The agrochemical complex would basically grow those plants that would allow us to act as a substitute. I have a digital 3D model that I'm mapping this out as well in Unity. I'm a video game developer, so I'm trying to visually map it out as well as map out the data. And this kind of maps out what some of the plants that we would need to have in order to have self-sustainable plastics, and also to generate soil. So there's certain nutrients that soil needs to be able to be function properly. And if we had these different baselines and use them as compost with worms, and you mixed it with regolith, that would gradually help to improve soil quality. So my agrochemical complex kind of dips into that topic of understanding. This is a flowchart for creating different bioplastics and epoxies from the materials that were just stated. Castor bean, sugarcane, soybean, cannabis, and flax are ideal candidates for this purpose. This is a flowchart for water, how we could go from having wastewater back to reclaimed usable water or potable water for plants. This is a visual demonstration of the wax Allmatter machine, which would basically grow the plants, have a small refining system, have a recycling system, and a 3D printer that could print wax components. This is something that could be emulated in analog stations. I'm looking for potential analog partners to develop parts of the Allmatter machine as demonstrations so that they could eventually be replicated on the moon. This is one that could be done relatively easy for low cost in comparison with some of the other more complex materials. I've already gone through this process at home for the most part without, growing soy plants and stuff like that, but from using recycled wax to manufacturing it and producing it, proving as a proof of concept that this can actually be worked and done it at home. As part of the Arcology Solutions work, we're creating an Arc education kit, and that will be part of one of the educational ways to teach people about closed loop systems. You can basically use broken wax, or you can use plants to go through the full material closed loop cycle, and you can teach that to kids because it's basically stove safe. you can melt wax on your stove. So with parental, advice or notice, you could kind of teach your kids how a closed loop ecosystem could work. And so through the ArcEducation kit that we're building, we could teach stuff like this. This is kind of a further refined understanding of the wax flows and different resources that we can use. Some of those we might have available in some contexts and some not. Lanolin from sheep wool, we might have on Earth, but we might not have on the moon unless we're having a sheep farm on the moon. Beeswax, we will probably bring bees with us into space. And in that case, beeswax might be accessible too, which has a wide variety of applications. These are some of the breakdowns of how we could use candelilla wax and soy wax as an example, just to get a kind of a feel for what could we use these for. If you have no understanding of it, you can use the waxes to create molds that you can then use in other industrial processes, or you could use it for sculptures, or you can use it for creating prototypes. Many different purposes that it can be used for. We don't think of it as, other than candle wax for the most part, but it actually is used in a lot of different applications. And in space, to protect cold metal from cold fusion, to actually have a wax casing on it can sometimes create a barrier so that you don't have metals contacting. Beyond that, you have the chemical factory, which would kind of expand on that, but with more industrial chemicals like sulfuric acid and things that are needed for industrial basis. If you need to produce these things, manage these things, it would be done in the chemical factory. Beyond that, we have the atmospheric separator, which is a type of cryogenic cooling unit, which actually does exist already. There's companies in the world that produce atmospheric separation units for oxygen, nitrogen, and there's ammonia separation. So we could use this technology within the colonies to actually filter the air system. So you basically suck all the air through a cold system that freezes the constituents and gets it to the point where it's liquid. And then you separate them based on their freezing level. So, for example, in petroleum distillation, they use a similar process, but it's with heating, called fractional distillation, where basically based on the different temperatures, you get different products that are separated. If you were to do the same thing with air, you could basically do the same thing and get nitrogen, argon, liquid oxygen, and potentially other things as well based on their freezing point or their liquidation point. So if we're able to have an atmospheric separator, that can help us with processing and storing and also filtering our air systems. Very important aspect. Once we have all of these wonderful materials at our disposal, the material manufacturing list, what it actually enables, gives us a lot of options. This means that if we can basically bring all of these machines to build the phase one and then ship the resources, we don't need to ship fasteners, bolts. We don't need to ship hand tools. We don't need to ship vehicle frames. We don't need to ship modular housing frames. We can produce all of these on site, and all we have to do is now figure out how much steel does that colony need? How much aluminum does that colony need on the basis of a colonist's personal needs? How much steel per person is actually required? So we can create a formula to actually figure it out. If, we're going to have 10,000 colonists go here, we're going to need 100,000 tons of steel. We're going to have 10,000 colonists, we're going to need 5 tons of copper. We can basically figure that out now using this machine as a framework. So that's kind of where my research is kind of digging now and looking at other people's work that have kind of dug into that data and trying to align it with the information that I'm pulling. So you could also use this kind of stuff to build railway components, to network with other mining sites. You could have using concrete and epoxies. You could start paving roads. You could have aluminum and polymers making maintenance carts. So by having these first 12 materials and having the manufacturing capacity to build their components and assemble them on site, we unlock so much capability with each phase that essentially by the time we get to phase 3 or 4, you'll be able to, as a colony, launch into space and access space-based resources. So at that point, if you can drop enough resources to get a colony up to the point of phase 3, they can become fully self-sustainable. And that's kind of what my aim is how do we figure out, how do we drop that seed that can then grow and produce new seeds? And so in that sense, that's what my research is that kind of aimed towards. And the manufacturing complex now would have a lot of different technologies and tools and require different people to operate them, or you could have telerobotic workers, or if you could automate the machines, it could go from being a dust factory to a full-fledged dark factory. But I would refer to the Allmatter machine in its early stages as a dusk factory moving towards dark factory status, where eventually you could move the workers above the industrial process into the arcology that kind of sits above the industrial base that's now fully autonomous. This would obviously take phases to develop, but my plan kind of maps out those phases so that, like I said, by about phase 3 of development, you would be able to produce robotics, you'd be able to produce AI, and be able to produce the fuel sources that would enable true self-sustainability. So manufacturing processes would have 3D printers, 3D printing farms that could print all of those said materials, assembly lines that would allow the assembly of those materials into more complex structures, microfabrication zones that would allow for, circuit boards, fine tools to be created, quality control rooms that would test, make sure that all the products are working. The electroalloying lab would be another important factor because electroalloying will allow for the creation of new novel alloys by layering metals on top of each other using electroalloying processes. One of our other members at Arcology Solutions, Breyer, is doing a lot of work with electroalloying, and there's a lot of potential developments that could expand in that direction. So as we kind of climb the phase tree, the electroalloying lab would be added and enable the creation of more complex alloys with multiple materials. For the novel material labs, there would be a lanthanide R&D lab, which would basically study rare earth materials. These are kind of an outline of some of the rare earth materials and what applications they are used for and where they are currently sourced, so that for mining purposes, we know where we would be able to order these from, or where you would want to set up mines that kind of feed into the Allmatter machine. Beyond that, we have the actinide R&D lab, which would basically do research on nuclear fuels and reactor components. A nanotech and metamaterial R&D lab, which would study nanomaterials and futuristic technologies. And this basically concludes my presentation about the Allmatter resource management machine and megastructure logistics engine. You can actually test the Allmatter machine as part of a game that I've created. On ChatGPT, I've created an AI called ArcCommander. And ArcCommander is a simulation that demonstrates some of the ebooks that I've written in a playable manner, where essentially there is a future cosmic republic that is oriented around an arc-centric model of civilization, where you can build arcologies, you can participate in arcologies, you can train for cosmic careers, you can become an exopolitician and practice cosmic foreign relations, and you can learn about the Allmatter machine. I have integrated the white paper for the Allmatter machine into the game so that people can play with, experiment with, and learn about this machine and use it as a digital twin that we can then learn from, build in the digital version that I've been working on, and then apply to the real world. So this is a technology that does exist in a digital sense now, but could be implemented in the real world and does have a digital testable component that allows you to understand how this would apply. On top of the logistics management system, I've also created something called the Terraformer Shipyard Arcology model, which is a terraforming model that basically installs biology on planets. So in coordination with the biological installation of terraforming, we also have the industrial installation of the industrial tree. So with these two technologies combined, we could enable cosmic civilization, the colonization of other planets, and the industrialization of space civilization. Thank you for watching my presentation. And if anyone is interested in collaboration, I'm open to doing so. I'm also open to collaborating and contributing to other projects within the space ecosystem. So please feel free to reach out and contact me. Or if you have questions, I will now open the floor to do questions.
Thank you, Andrew. Very ambitious set time. Peter Schubert has a question.
Sure.
Andrew, very compelling and comprehensive vision, very interesting, and I love your graphics. You probably know about the Millennial Project from 30 years ago, which showed how to conquer the galaxy in 8 easy steps. And some of the criticisms levied against that work were that how are you going to get the governments going? If you've got a great vision, how do you get other people involved? It sounded like you started to get involved with the government, and that didn't work out. I'm super curious if you could tell us a little bit more about that story.
So, in short, in Canada, I originally ran in 2015 to create an upstart new political party called the Cosmic Pirate Party. So we were a branch of the Pirate Party that I wanted to advocate that we should commandeer the cosmic narrative because nobody was talking about space. In England, there's a guy called Lord Buckethead who used to run for political office, and he wears a spacesuit and talks about galactic imperialism. So I said, after 2014, I ran for provincial MP and learned a little bit about the ropes and said, you know what? I want to talk about space. I want our federal government to talk about space. And we've got this guy over in England that talks about space, but he's kind of a joker comedian. It doesn't really advance the issues. But why not take that from a serious perspective and say, well, there's Lord Buckethead and now there's Star Captain Dread. And I'm going to talk about cosmic republicanism instead of galactic imperialism. That's a great contrast. And, well, the government of Canada, being a monarchy, they seemingly maybe didn't like that. But I now live in America. I'm now an American citizen. And our commander has actually earned the endorsement of a Space Force ambassador on behalf of the Pentagon and Space Command. So I now write as part of the think tank. I'm now, like I said, free to work and free to build this machine, which I'm aiming to incorporate the Allmatter Corporation LLC within the next couple of months to produce this framework that would essentially provide a solution for the Artemis Accords, so that we have a roadmap that from 55 countries, we now have different technologies that we require to build this roadmap, and we have different companies that can compete for fulfilling that role. So now it's a matter of, can we find all the pieces to fill into this roadmap? I've created the roadmap. Now we just need to plug in all the pieces. Some of those pieces already exist. The atmospheric separation unit, there's already 10 companies that produce these. So a huge section of the facility, we can now say, well, if there's any company within the entire Artemis Accords network of 55 countries that can build this system for this cost, we now have a budget.
Shall we let Stuart in for a quick last question?
Sure.
I was thinking about your presentation yesterday, Nicholas, and kind of mapping out how things go, and then tying in what Andrew's talking about. And I'm thinking that the products that are essential to start with in a lunar colony, that's something to figure out. Like it's not like we're not gonna have everything up there that you can go into Walmart and buy, right? There's a ton of products there that aren't going to be there, and so it'd be nice to have a map of, okay, what are the essential short-term or near-term products that we have to have, like some medicines, shovel maybe, or I don't know, but I don't know exactly what they are, but yeah, that's a very important step to figure those out.
So this is kind of what I was trying to figure out, is that what we could produce on site with these materials, and a lot of these things that it would save us a lot of time and a lot of energy to be able to actually do that on site. I'm trying to see if I could find the manufacturing one here. This is the list here. So as an example, some of these things would be kind of complex to store in the spaceship. if you try to stack boxes versus stacking flat sheets, you're gonna be able to fit more volume in, right? So basically what we're gonna want to do in the end is pack starships full of resources and have another one that sends the manufacturing equipment. Once the manufacturing equipment's there, you no longer need to send the actual physical equipment, which takes up more space. Now you just send compacted material in a safe, storable manner, and then they can unpack it, ship it through their manufacturing process, and they can take an ingot and turn it into 10,000 screws. And, you know, it's going to take up more volume as screws versus the ingot, right? So that's kind of the idea, is to ideally make it so that we don't have to ship products anymore. We're shipping blueprints digitally across the internet, and then we're having in situ resource management, and then colonies basically just say, well, we don't have aluminum, we don't have copper, we need steel. You know, can Mars send us 100,000 tons of steel by next month? Okay, well, that's what the freighters are going to need to send, and the freighters could be built by the shipyard to mass transport this material.
Ambitious vision there, but we need to cut for the next presenter.